So if we're looking at importance through the organic chemical industry lens, the single most important reactions of alkenes is polymerization. What's a polymer? Okay, it's from the Greek words poly, meaning many, and meros, meaning part. So it's any long chain molecule that's synthesized by bonding together many single parts. These single parts are called monomers. Mono means single, and meros means part. So there are two types of polymerization. Last class, we talked about the addition reactions. So we had something like this, and we added hydrogen to it. And that double bond in the middle was broken with hydrogens added to either side of the carbon atoms. So you have a saturated bond now. So an addition reaction is actually how plastics are made. So your plastic bowls, cups, Tupperware, all of that. Your second is condensation. So it uses two different monomer addition reactions that can be the same monomers, but condensation reaction uses two different monomers that are joined together through either esterification or amidation, and you get a polymer plus water because it joins between a hydroxide group and a hydrogen to form an ester or an amide. Polymers are extremely important in our life. We use them in our clothing, and as building materials, as eating utensils, so many different things. So if we look at different different polymers, you can see here that you take just this portion and you get them connected to each other repeatedly. And this section in the brackets here, and here you can see, that's a repeated portion. The N, you put whatever number it is that it's repeated. And so it's just this long line of monomers joined together in repeat fashion. Okay, let's practice a little bit from last week. What's the correct IUPAC name for the compounds shown below? So remember, we count the number of carbons and we start with the one that has the closest substituent. So here we actually have a substituent, bromine, right there. So we'll start 1, 2, 3, 4. So our base name is going to be pentene. It would be pentane, but we had that double bond right here. So it's going to be pentene. Where is that double bond? It starts at the 1, the first carbon, carbon number 1. So 1 pentane. Now I look at my substituents. They're both bromine. What carbons are they on? They're on 1 and 3. So it's 1, 3, dibromo pentane. Or not pentane, because pentane would be 5. It'd be butane. So 1, 3, dibromo butane. So that is C right here. What is the correct IUPAC name for the compound shown below? 1, 2, 3, 4. This is also going to be butene. Where is that double bond? It's on the first carbon. So it's 1 butene. Hopefully you did all right with those. I know practice, practice, practice is what we've got to do. Okay, let's talk about polyethylene. Now, this is a type of plastic. You have two types of polyethylene. You have low density polyethylene and high density polyethylene. Low density polyethylene is highly branched. So it's a polymer chain that's kind of like a branch of wood. You want to stack them, but it's hard for them to actually lay flat. They're all haphazard with all of their branches. And so they don't pack well. Instead, because they don't pack well, they have really, really, really weak London dispersion forces between them. So these will soften and melt above 115 degrees Celsius. That's pretty low. Approximately 65% of all LDPE is used for the production of films for packaging, like your bubble wrap, and for trash bags. That's what most of the LDPE is used for, to give you an idea how weak those forces are, how easily you can break those plastic bags. Now, high density polyethylene has very minimal chain branching. So it's more like this. So you can lay these flatter against each other, and they're closer in proximity. And if they're closer in proximity, they're going to have more opportunities to create those London dispersion forces. So they're going to be stronger, which means they're going to have higher melting points than the LDPE and can be used for, they're more durable because they can be used for heavier materials. So this is what your jugs and bottles are made out of. Your plastic water bottles, your milk jugs, your pop bottles. That's what we use for our LD or HDPE. Your LDPE, it's just really thin sheeting. So this is kind of the process to make it. And with the HDPE, you can put it into a mold to make your bowl or your jug or whatever plastic object you want to make for it to be formed. Okay, moving on from alkenes, we're now going to talk about another component called an alcohol. Now, right here is the functional group for an alcohol. It's your hydroxyl group, and it's bonded to a tetrahedral carbon. Methanol is the simplest alcohol. When I worked in a pharmaceutical lab, we used methanol for most of our solvents. It was a very good solvent. It's the simplest alcohol, and it did a wonderful job in our HPLCs. Now, physical properties of alcohols. You have the carbon and bonded to the oxygen, which is polar, because oxygen is more electronegative than carbon. And then you have this hydrogen here attached to the oxygen, and we know that oxygen is much more electronegative than hydrogen, so that is a very polar bond as well. This is why alcohols are water soluble. So here you have a 3D image of methanol if you were curious as to what it would look like. So here you can see the hydrogen bonding because of that polarity with the OH and the carbon, and you've got those dipoles here, because you have this, they're able to hydrogen bond. That hydrogen bonding elevates their boiling and freezing points. So you can see here that we've got methanol and ethane. This is just an alkane, but here's your alcohol. Similar molecular weights, but the boiling point is way different. You can see how much higher it is. Same thing with butanol and pentane, similar weights, but butanol has a much higher boiling point than the alkene, corresponding alkene of a similar molecular weight. So alcohols, because of that hydrogen bonding, has higher melting and boiling points. One of the reactions that alcohols can undergo is dehydration. Now, dehydration, D means to take out or less. Hydration is water. So you're eliminating water from the adjacent carbon atoms to give an alkene. So right here, if you wanted to have a dehydration, it would take this hydroxyl group and one of these, and you'd become an alkene like this. It just removes a water from that molecule. You have tertiary, secondary, and primary alcohols. I'm not going to ask you to remember what type of reaction each one undergoes, but I did want you to know that dehydration is usually brought about by heating the alcohol with either 85% phosphoric acid or concentrated sulfuric acid. So dehydration typically needs heat and an acid in order to occur in an alcohol. But dehydration results in a double bond because you're removing that water molecule. Here is an example of dehydration. You've got ethanol, and you are doing acid catalyzation with sulfuric acid at 180 degrees Celsius. And you create ethylene because this water molecule and this hydrogen have been taken, and water. Or you could do cyclohexanol. You take one of these hydrogens plus this hydroxyl group, acid catalyzation, and you get cyclohexene. All right, that's it. I hope you guys have a great weekend, and I'll see you next time.